Yay, you wouldn't believe what it took to get to this point. Okay, so remember, sorry, repeat it. So NPR permutations is where order matters. The formula is on your formula sheet. N factorial over n minus r factorial. Combinations, NCR, or number over number in an elongated set of brackets. Do not put a fraction bar in there. It's not a fraction. N factorial over n minus r factorial. So in both cases, there are a total of n objects, and we are arranging r of them at a time. In the combination, order does not matter, and that's why we're dividing by the r factorial. That will take out all the different orders of those r objects. So your book committee needs a group of 6 girls and 4 boys. Note the word and. Right, so 6 girls, we have 8 to choose from. 8, choose 6, right? Order doesn't matter, combination. That's our girls. 8, choose 4. Works out to 1960. If they decide to line the students up in a row with the 6 girls first, and then the 4 boys, right? And remember, and then, and is multiply, or is add. So if we are saying or, we're going to add things together. If we are saying and, we're going to multiply. How many different arrangements? So we could use the fundamental counting principle, in which case we're going to put down 10 blanks, and we're just going to say, I've got my 6 girls first, 2, 4, 6, and then the 4 boys. And for the girls, I have 8 choices for the first, then 7, then 6, then 5, then 4, then 3. And for the boys, 8, then 7, then 6, then 5. Now, that should be the same as saying 8p6. So I have 8 girls. I want all the arrangements of the 6 of them. And then, so times 8p4. Which is, need a calculator. Now, permutations, there's always more permutations than there are combinations. Ooh, calculator is out of frame. That helps. Okay, let's put it. So 8 math over probability. The P is 2, 8p6. And legit, I can just put them next to each other, right? It's going to know that it's 8p4. Right? And it's a little bit bigger, as in 33,868,800. No, there's always just a couple more permutations. Okay, there's a lot more permutations, right? Distinct arrangements where the order matters. Dodgeball tournament allows 12 players to start each game. If the Warriors have 20 players, how many different groups of starting players could they have? Okay, so work that out. I'm going to pause this while... Okay, in part A, does the order matter? No. So I'm just going to write 20C12. Right. Usually when I'm doing combinations, I'm going to multiply together. Then I like to use the brackets because it's a little more compact and a little easier to read. We've got this times this. And 20C12 is 125,970. If the first group of starting players has to stand in certain positions in the end zone, how many arrangements are there? Okay, so if you have to stand in a certain position, what does that mean? Order matters, right? So this becomes 20p12. So we know that in any given situation, there will be more permutations than combinations. In this case, there's a few more, because it works out to 60 trillion, which is a little more than 125,000. Okay. It's right. Basically, the difference between the C and the P is in 20C12, we're dividing by 12 factorial to take out all those different orders. Right? And 12 factorial is going to be like 300 million-ish. I'd go 2. I mean, when we're talking numbers that big, does it really matter what follows that? So if in doubt, round to 2 decimals. Okay. Otherwise, it should say, given a standard deck of 52 cards, how many different 5-card hands can be dealt that contain at least 4 black cards? Okay, so before you do this, I want you to say or write down, okay, how many black cards could there be? So we could have, if we've got at least 4 black cards, how many black cards could we have? Could have 4 or 5. Yeah, you don't say it too loud, it won't have 4, which is fine. Now, let's get a little more specific. If I have 4 black cards, then what else do I have? 1 red card. So I have 4 black cards, or 5, nice 5, or 5 black cards. Now it has to be a 5-card hand, so if I have 4 black cards and 1 red card, right? It says multiply, right? 26 choose 4 is the way of choosing 4 black cards and multiply 1 red. 26 choose 1. Or we have 5 black cards, or plus 26 choose 5. And you don't need this. You likely won't see that, say, on the diploma in this scenario. They would just go 26 choose 5. I always like my top numbers. See, in both these cases, the top numbers add to 52, which indicates I'm taking account of all 52 cards, and the bottom numbers add to 5, which says of those 52 cards, I'm going to get 5 of them, right? And that works out to 454,480. So at least 4 black cards, right? When we get at least, at most, whatever, we got to try. I like to just say all the possibilities, right? There are 4 black cards and 1 red card, or 5 black cards. And no red cards if you want. How many different contain less than 3 hearts? How many hearts could you have if you have less than 3 hearts? Yeah, so you could have no hearts, or 1 heart, or 2 hearts. So another way of saying less than 3, you could say no more than 2. And if it had read no more than 2 hearts, you would have said 0 hearts, or 1 heart, or 2 hearts. Right. So just make sure that you're interpreting the wording correctly. So 0 hearts, or 1 heart, or 2 hearts. How many hearts are there? So there are 13 hearts. If you are heartless, then it's 13 choose 0. How many cards are there that are not hearts? 39. How many of them will we need? So 39 choose 5. So 13 choose 0. Top numbers add to 52, right? There's the 13 hearts, the 39 non-hearts. We want no hearts, 0 hearts, so that's 0 hearts and 5 cards from the remaining 39. Or 1 heart, so or plus 1 heart you're not heartless. You're just human, 1 heart. 39, choose 1. Or plus 2 hearts. Now you're the doctor. And 3 cards from the remaining 39 cards.
39, which the amount of cards we have to minus the amount of cards.
Yeah, so there's 13 diamonds, 13 spades, 13 clubs. There are 39 non-hearts, not a heart. And this is 2,357,862. Yes.
Do you have the whole thing in perspective, or can you do that?
Well, so the minus thing would be doing, I could have 3 hearts or 4 hearts or 5 hearts. In which case you're working out 3 things and then 1 more, which is everything. So it's actually less work. In the grand scheme of things, we're talking 30 seconds difference between the 2 calculations, but there's no clear advantage to doing it the other way. We'll do that later on, where we say, now hang on a sec, right? So if you think, I got a 5-card hand, then what you should be thinking is, I could have no hearts, or 1 heart, or 2 hearts, or 3 hearts, or 4 hearts, or 5 hearts. Right? So there's 6 ways that can happen, right? None, 1, 2, 3, 4, or 5. Now, if we want less than 3, that's 0, 1, or 2. If we do it the other way, we would have to say, well, there's 52 choose 5 ways of getting a 5-card hand from the deck. From that, we will subtract the ones that have 3 hearts, or 4 hearts, or 5 hearts. So it's actually going to lead us to doing 1 more calculation than if we do it this way. So it's sort of 6 of one, half does the other. Now remember, there's only 2,598,000 whatever. There's like 2.6 million possible hands. So most of them will contain less than 3 hearts. So 2.4 million, rounding. How many different 5-card hands contain at least 1 diamond? Ah, now what you said, right? So how many diamonds can you have? 4?
1, 2, 3,
Or none?
or is it at least 1?
No. So let's think about just possibilities. Forget the card right now. I can have 0 diamonds, or 1 diamond, or 2, or 3, or 4, or 5. We want at least 1, which is 1, or 2, or 3, or 4, or 5. What we don't want to do is add up 1 diamond, 4 non-diamonds, plus 2, plus 3, plus 4, plus 5. Because we say, well, there are 6 possibilities, right? No diamonds. So what we don't want is no diamonds. Double negative. So if we take all possible hands, subtract from that the one that has no diamonds, then we are left with at least 1 diamond, right? We're left with there's 1, or 2, or 3, or 4, or 5 diamonds, which can also be expressed as at least 1 diamond. So the other way to work this out is 13 choose 1, 39 choose 4, 13 choose 2, 39 choose 3, 13 choose 3, etc., etc. Right? And they'll both give you the same answer, which is 2,023,203. So of the 2.6 million, right, most of them will contain at least 1 diamond. There's basically only about 570,000 that have no diamond. How many different 5-card hands can be dealt that contain a pair of 10s? Pair of 10s. Okay. See if you can figure this out. If you're watching this on video, I'm just going to pause. You should pause now, figure this out, and then come back. So how many 10s are there? Or how many of them do we need to make a pair? 2. How many not a 10 are there in the deck? 48. How many of them do we need? So if you imagine you got the 52 cards in your hand, I got a deck of cards. I'm going to separate out the 4 10s, put that in a pile on the left, and on the right I'll put the other 48 cards. Just sound effect, right? They can't see anything. And from the 4 cards, I'll say, well, I need 2 of them. That's 4 choose 2. 4 choose 2 is 6 different ways. Let's verify that. So let's say I've got the 10 of hearts. So I compare that up with the 10 of diamonds, 1, 10 of clubs, 2, 10 of spades, 3. That's everything with a heart. Take away the heart, so the diamond can go with the club or the spade, and then all that's left after that is the club and spade. Right? Because we don't care about order. So when I say the 10 of hearts, 10 of diamonds, I don't care about the 10 of diamonds, the 10 of hearts. Right? So there are 6 ways. And then obviously there's a whole bunch with the 48 choose 3. Gets us to 103776. Now, there's nothing special about 10. So that could be a pair of aces. That could be a pair of jacks, a pair of queens, a pair of kings. If you play poker. Multiply that by 13, that's the number of possible pairs there are in a 5-card hand. Right? So when you're dealt out a 5-card hand, of the 2 million, well, what is this? 52 choose 5, right? Is the 52 choose 5. Of the 2,598,960, we got 103,776. That's one particular rank, right, which is 10, but there's 13 ranks. So to get a pair of the 2,598,960 different possible hands, 1,349,088 will be a pair.
So the question would say, if it's named at least one pair, and we will be forced to choose more.
So at least a pair of 10s, but then something higher, like 3 10s or 4 10s.
So it depends, like for this one, 4 choose 2.
Yeah.
4 choose 3 does that at least one pair. There could be 2 pairs in one pair.
Yeah.
Okay, so if it said at least one, then we would choose the 4 choose 4.
Yeah. So when we get into probability, the next unit, we'll be looking at poker hands. So for those of you that play, great, you'll be able to look at it and say, oh, okay, this is why the hands are ranked the way they are. Right? So like the lowest thing that you can get is a high card. You don't have a pair. And that happens a whole bunch. Right? But a pair, which would be that 1,340,000, that's about half the hands, right? 1,349,000. That's about half the hands will be one pair. Exactly one pair. Exactly one pair. Then the next thing we move up to is 2 pairs. Then 3 of a kind. And each time we move up, there are fewer and fewer ways of getting that, right? Which is why it's a higher ranked hand. It's less likely to happen. So let's check out 3 of a kind. So how many different 5-card hands could be dealt that contain 3 kings? All right, so same deal, right? Well, then we're going to go 4 choose 3 and 48 choose 2. Which is, let's look at that. 4 math, over there, 3, 4 choose 3, up, times, I'm going to put times in, you don't need it, but why not, 3, 48 choose 2, So 4 kings is 4,512. 3 of a kind. Sorry, 3 kings. So 3 kings. So there's 13 ranks, right? We could have 3 kings, or 3 aces, or 3 twos, or 3 whatever. So it's 13 times this. So the number of 5-card hands that contain 3 of a kind is 58,656. That is a lot less likely to happen than one pair, right? One pair is 1.3 million ways, right? Or a little over that. 3 of a kind is only 56,000, 57,000. You get up to a royal flush, how many ways are there getting a royal flush? 4 ways, right? So all of this counting is needed to do any of the probabilities, right? Especially if we're counting cards, not like that counting cards, but counting the ways the different hands can happen. I'm not going to sit there and deal them out, right? I'm not going to list all 1.3 million ways of getting a pair. Okay, we want to be able to count them. This is how we can count them. Basketball team of 11 players is to be chosen from 17 available players, which includes Jeff and Brett. In how many ways can this be done if Jeff and Brett both must be selected? Okay, so we want them both on the team. Figure it out. I'll pause. We'll pause. So one way we could do this, we could say, there is one Jeff and we need one of them. There is one Brett, and we need one of them. There are 15 players remaining, right? So imagine the 17 players are standing out in the hall. I send Jeff and Brett into the room, and then I say, okay, how many ways of the remaining 15 players? I need 9 of you. Don't do 1, choose 1, right? 1, choose 1 is just 1. So if all you wrote was 15, choose 9, good enough. Right? Good enough. I mean, you can follow what it is you're doing. If you were asked to explain it, then just say, I'm sending Jeff and Brett, they're being chosen, so I have 15 players left, of which I need 9. Right? That would be the words I put down, then go 15, choose 9 equals 5,005. Jeff and Brett maybe don't necessarily get along, so they cannot both be selected. How many ways can we do it where they are both not selected? So think about all the different ways that are possible and decide how you want to handle this. And then handle it. And we'll pause. So let's examine all the possibilities, right? We've got Jeff, Brett, 15 other people. Now, here we've got Jeff and Brett both selected, right? Let's call that JB, the outcome where they're both selected. Now, usually in math, when we put a bar over something, it says not. So that's neither Jeff nor Brett, right? So neither of them are selected. So they both can be selected. That's actually part A. Neither of them can be selected. What are the other possibilities? One of them. Which one? So let's start with Jeff is, Brett isn't. So there are 4 possible outcomes, right? When we're talking about these 2 players on the team. They're both on it. Neither of them are on it. Jeff is, Brett isn't. Jeff isn't, Brett is. Okay, so both cannot be selected is these 3 ways. Or, and I'm not talking about using the plus operation, or we could say, listen, there are 17, choose 11 ways of making up this team. If from that we take away the ones where they're both on, then what's left? the ones where they both aren't on the team. But that doesn't mean both of them aren't on the team, right? It means both of them aren't on the team, or one of them is, but the other one isn't. Okay, so if we subtract, remember, 4 outcomes. We're just subtracting one of those outcomes, which is both of them are. What's left? Both of them aren't, one of them isn't, the other one isn't. One of them is, the other one isn't, etc., etc. Which works out to 7371. Which would be the same as you doing not Jeff, not Brett, and from the 15 remaining players, I want 11 of them. Or, yes, Jeff, no, Brett. Or, no, Jeff, yes, Brett. Notice in all 3 of those instances, the top numbers add up to 17. Right? We got a Jeff, we got a Brett, we got the other 15 players. The bottom numbers add up to 11 because we are choosing a total of 11. Do not work out any of the 1, choose zeros. They're all 1. Don't work out the 1, choose 1. That's also 1. So it's just 15, choose 11 plus 2 times 15, choose 10. Prove it. All right. I hope this works. So it's 15, choose, which is 3, 11, plus, oh, don't do the plus down there, plus 2 times 15, choose, what do we need, 10. And the answer is 737. I hate to be doing this live. I come to something fast. I'm going to be shortening it. But the reason this is being recorded, it's actually due to the next example. It's like, oh, there's mistakes in this next example, right? So you can work it out both ways. What happened to the one? You can work it out both ways, right? Either way. And it's not a big deal one way or the other. It's just already having the first number, the 5005, it's easier to work it out that way. But, big deal, 15, choose 11, plus 2 times 15, choose 10. So it's not a huge investment of time. How many arrangements are there for the letters monotonous if there are no restrictions? And we know there are never no restrictions. When there are repeated letters, that has to be taken into account. So how many arrangements or different arrangements? And anytime we do letters, it's permutation. But not that kind. So figure it out. We'll pause. Pause for a moment. So how many letters are there in total? 10. So 10 letters can be arranged 10 factorial ways. But what? There are 4 O's, so we need to take out, this is a permutation with a repetition. And there are 2 N's. So permutations with repetitions are always done this way. What's the total number of things? And also in a permutation with repetition, we're never going to say, what are all the 3-letter arrangements from this group of 10? Because there's too many possibilities you got to look at. Well, what if they're all O's, right? Because then that can only be done one way. Or if 2 of them are O's and then the other letter is different. What if 2 of them are N's? There would be just way too many cases to look at. So that's beyond the scope of what we're doing. So with this repetition, we might say begins with a T, which is the next one. But let's do this one first. 75,600. How many of those begin with a T? Yep. No. Because how would you do it?
I don't know. I don't really understand.
So you'd have to go 10p10 divided by 4 factorial 2 factorial. So when we do a permutation with repetition, it's always just, so if there's 10 things, right, if there were 10 different things, we could say 10 factorial or we could say 10p10, right? So here, we just say, all right, it's 10 factorial. And the reason we say that is because we know we're dividing by the repeated things, so I don't want to mix sort of like 10p10 and then on the bottom put factorial. I'd rather just keep it all in just factorial notation. Begins with a T. So what I like to do is just let's write them back out again. And then what am I going to do? I'm going to take out the T. It begins with a T, so that's not in there. Okay, what's left? Well, there were 10 letters. The T is gone, so there are 9 letters left. That's 9 factorial, but 4 of them are O's, so we divide by 4 factorial. 2 of them are N's, so we divide by 2 factorial. That is going to be 1/10 of the number above, right? Because the number above is 10 factorial, and 10 factorial is 10 times 9 factorial. And whatever, either way, just work it out. And you get 7,560. So basically 1/10 of the arrangements, because the T now is in the first place, and then we have those 9 letters left. Each arrangement begins with an O. Give that a shot. So I do the same thing. I just like to write it out again, right? I know you think it might be boringly repetitive to write it out again, or monotonous, but write it out. Get rid of an O. What's left? Got 9 letters. How many are the same? Oh! There's only 3 O's remaining. Right? And what else? 2 N's. So 9 factorial over 3 factorial, 2 factorial. Now it begins with an O. Could those arrangements also begin with 2 O's? Is that a possibility? Or 3 O's? Or all 4 O's? So when we work out begins with an O, we're just saying, I don't care what's next. It doesn't matter. So another way you could think of that, begins with at least 1 O, but you wouldn't do it any differently, right? It begins with at least 1 O. It means it just doesn't matter what's next. As opposed to, begins with exactly 1 O. Okay, try and figure that one out. I'll give you a minute or 2. We'll pause. Okay, so this is one of the students came up with, was saying there are, wait, hang on, I'm just going to write the letters down. I know, it might get a little repetitively boring. Just keep writing the letters down, but. So it begins with exactly 1 O, so we'll take the O out. And now we will say there are 1, 2, 3, 4, 5, 6 letters left. Right? We have 6 letters left to choose from for the next letter, so that it is not an O. And then, so that's any one of those letters. So there were 10 to begin with, 9, so now there's 9 because of the 1 O. So now there's 8 letters remaining. But we've got to take out the order of the 3 O's, the 3 remaining O's, and the 2 N's, right? So we have 6 times 8 factorial over 3 factorial, 2 factorial, which is 2160. Now there's another way to do this. They aren't even like us as well. But we'll do it anyways. So we've got, in part C, we've got each arrangement begins with an O, but it means one O, or two O's, or three O's, or four O's, or five O's. So if we want to begin with exactly one O, what we don't want to do is begin with two O's. So if we figured out the ways that you could begin with two O's, so let's kind of squeeze this in here. So say begins with two O's, which means two O's or three O's or four O's, right? So let's write out the letters. Begins with two O's, so get rid of the two O's, two of the O's. So say we have 8 letters left, 2 of which are O's and 2 of which are N's. So that's 8 factorial over 2 factorial, 2 factorial, which is 40,320 divided by 4, so that's 10,080. So 1080. 10080. So if we took the 30,240 that begin with 1 O or 2 or 3 or 4, and from that subtracted the ones that begin with 2 O's or 3 or 4, then what we'll be left with is the number that begin with exactly 1 O. So 0, 1, 14, 6. That's a 1, that's a 0, that's a 2, O, 1, 6, O. Always ways better, but that's another way to do it, right? Each arrangement begins with exactly 2 O's. Okay? Figure it out. I'll give you some time. So let's start this out by rewriting the word. Okay, so we give it exactly 2 O's, so I'm going to get rid of exactly 2 O's. So the third letter can't be an O, so we have 1, 2, 3, 4, 5, 6 choices. That's 6. And then one of those is gone, so we now have 1, 2, 3, 4, 5, 6, 7. But 2 of them are N's, even if the N ended up here, and 2 of them are O's, and I'm told that that's equal to 75, 60. I don't know, I believe you. Yeah, right. I don't believe you again. You lie. So there we go. Really what's happening is whether the N is here or not, we're just going to take out the order. Like somewhere in there are 2 N's. So we need to divide those arrangements by 2 factorial for the N's, as opposed to worrying about, well, is the next letter an N and then there's no repeating, and then we don't have to worry about that, right? So we just 6 letters that could go in second place. That includes the 2 N's. The 2 N's are somewhere in this number, so we divide by 2 factorial, and then 2 factorial for the 2 remaining O's. So another way to do it is to say, look, we know that there are 10,080 that begin with 2 O's, or 3 O's, or 4 O's. So if from that 10,080, we take away the ones that begin with 3 O's or 4 O's. So just basically do this. Just say begins with 3 O's, right? Which means 3 O's or 4 O's. So we write it out again. And we get rid of 3 of the O's. Okay, so 3 letters are gone from 10. That leaves 7 letters left. So 7 factorial. 2 of them are N's. Right? The O's, there's no repetition now, because the 3 O's are gone. Right? We put them down. 7 factorial, we put them down, but could be bad. So that's 5,040 divided by 2, which is 2560. No, 2570. 7 factorial. 7, math. Factorial divided by 2 factorial. I'm not going to put the factorial in there. 2520. 2520. So if we take the 10,080, if we could write 10,080 minus 2520, we got a 0, we got a 6, that becomes a 9, that's 10, that's 5, that's a 7, 5, 6, 0. So either way it works, right? We can do the ones, we know there are 10,080 to begin with 2 O's or 3 or 4. From that we subtract the ones that begin with 3 or 4, and we are left with the ones that begin with exactly 2. Okay, per way easier. But both ways work. What if it ends with all 4 O's? So, for the last time, I'm going to write the word out, because it's getting rather... And I got 6 letters, 2, 3, 60. So there are 6 letters remaining, 2 of which are the same. 6 factorial over 2 factorial is 3, 6. Okay, any questions? Number 6. And we've done something very similar to this, so okay, give it a shot. Do A. Okay, exactly 3 web-based. There are 5. Choose 3. And we need 4 journalists, right? So that's 1 down here to make 4. We have 7 print journalists here. 5 choose 3 is 10. And 7 choose 1 is 7, so there are 7. At least 3 web-based. So how many web-based are there if there are at least 3? So there could be 3 or 4. That's it. Right? There's only, we are picking 4 journalists total. So we don't need to get fancy about it, right? There are 3, so 3 or 4. So what's that translate to? So 3, 5 choose 3. Top number is always going to add to 12. Bottom number is always going to add to 4. Or 4. You do not need to write the 7 choose 0. I'd like to, because my top numbers will add to 12. My bottom numbers will add to 4. We already worked this out. That's 70. 5 choose 4 is 5. So 75. Good. At least 1 print journalist. So how many print journalists could there be if there's at least 1? 1 or 2 or 3 or 4. Ignoring everything, what's the total possible number of different ways we could get a print journalist? None, or 1 or 2 or 3 or 4. Okay. So there's 5 things, but we want 4, the 1, the 2, the 3, the 4. So what we'll do, let's take all the ways of doing it, which is, all right, just forget there are 12 journalists, I need 4. From that, let us subtract the ways where there are no print journalists. And what are we left with? Every other possibility, right? And there are 4 journalists, so there are 5 ways to choose them, which is none, or 1, or 2, or 3, or 4. We'll get rid of the none, and we will be left with 1, or 2, or 3, or 4, which will be at least 1. Okay, I'll cross that out. Underline that. At least 1. And what is it? 495 minus 5. 490 waves. All right, we're good.